Welcome back, everyone. In this unit, we're going to find out how we can obtain full wave rectifier. So what is full wave rectifier? First of all, let's describe these things in terms of half wave rectification. Let's say we have a diode circuit consisting of a diode and a resistor in series. And then we have an AC signals as VI. And we already learned that. So this circuit is going to allow the positive half cycle to pass through, but it is going to block the negative half cycle. So output would look like this, just roughly. So that is our half wave rectifier. So half wave rectifier allowed the positive half cycle to pass through, but it blocked the negative half cycle. So we don't have any negative half cycle there. So what is the limitation of this thing? The limitation is that we cannot use the energy that is provided by the negative half cycle, because when it comes to supplying energy, both positive half cycle as well as negative half cycle is supplying the energy. So we're going to have energy associated with this positive half cycle. We're going to have energy associated with this negative half cycle. So that means if you have an appliance, for example, a bulb, which is glowing, it is glowing due to the energy supplied by this positive half cycle, and also due to the energy supplied by this negative half cycle. So now that you have blocked the negative half cycle, so this energy is lost. So we want to tap into this energy as well. And at the same time, we want to have these things rectified. So that means I want to have a rectified signal. That means our signal is oriented in the same direction. Let's say in this direction. At the same time, we want to keep both the half cycle. So in that case, the output should look like this. So that is our full wave rectification. Or full wave rectification. So that means both positive half cycle and the negative half cycles are in the same direction. So in this unit, we're going to learn how we can obtain a signal like this. So there are two types of full wave rectifier circuits. One of them is called full wave bridge rectifier. Another one, full wave rectifier with center step transformer. Center step transformer. So at first, we're going to describe the full wave bridge rectifier. So this is the circuit configuration for full wave bridge rectifier. In full wave bridge rectifier, it consists of 4 diodes, and the orientation of the diode is like this. The D1, D2, D3, and D4. And this is the resistor connected between these 2 points. R is the resistance, and the output voltage is measured from across the resistor. So this is the input voltage, input signal that we are going to apply. So notice the orientation of the diode. If you notice, D2 and D3, they are oriented in the same direction. So in this direction, in this direction. And if you want to keep the signal to your left, if I want to keep the signal to your left, so this is the signal I'm keeping to my left. So in that case, it's no the clockwise direction. So D2 and D3 are in the same direction, oriented in the same direction, and clockwise direction. How about D1 and D4? They are also in the same direction, but opposite to D2 and D3. It's upward direction, or you can say anti-clockwise direction. So that's the observation we have need to make. Again, we are going to analyze the circuit for this signal. This is a sine wave with amplitude Vm. So in order to analyze the circuit, we're going to apply the same steps that we applied to obtain half-wave rectifier circuit. First of all, so we need to determine the transition state voltage. So step 1, voltage. So which means that the value of the voltage at which transition occurs. So that means if the signal is fluctuating between Vm to minus Vm, at what value of Vi we have a transition of the diode. So in this case, we are going to do it over half cycle by half cycle. First of all, we are going to consider the positive half cycle. So in that case, we have t is greater than 0, less than t by 2, Vi is greater than 0, and positive half cycle. So first of all, we're going to analyze the whole circuit for positive half cycle only. Okay. So let's say we have the positive half cycle. Now we have 4 diodes. And like we learned in our diode DC analysis, that if there is a single voltage source and there is more than one diode, if any diode appears to be reverse biased, will be reverse biased. So we have a single voltage source, which is Vi, and there are 4 diodes. So in that, we notice D1 and D4 appears to be reverse biased with reference to this signal, because N side and the positive terminal in the same side, P side and the negative terminal on the same side. However, D2 and D3 appears to be forward bias. So that means we can reduce the numbers of diodes. So D1 and D4 are gone. So next thing would be, we're going to determine the transition state voltage. So we know at transition, voltage across the diode is 0.7 and the current ID is equal to 0. And since there are 2 diodes, D2 and D3 are in series, you see now we have the connection like that. If I draw it here, if I draw the simplified diagram, so D2 and the resistor and D3 plus minus Vi. You see, this is how it looks like. Positive terminal, then D2, then the resistor and D3. So if you want to determine the transition state voltage, so we have to pass through 2 diodes. we have to pass to two diodes, the transition state voltage will occur 0.7 and 0.7. So if we redraw the circuit for transition, Vi plus minus plus minus plus minus R, and let's say the current is I, which is we know is 0. If I apply KVL, then we get plus Vi minus 0.7 minus IR minus 0.7 equals to 0. So IR equals to 0. So that gives us Vi is equal to 1.4. So that is our transition state voltage. For positive half cycle. So that is our transition state voltage. So next, what I'm going to do? Next step is to draw the transition state line. So this is our transition state line. Transition state line. And we draw it at Vi is equal to 1.4. And what does transition state line tells us? Transition state line gives us the boundary between the on state of the diode and off state of the diode. Okay. So since the diodes are oriented in clockwise direction, we know that for the range of voltage above the dotted line, diode is on. And the range of voltage below the dotted line, diode is off. So that means for all these voltage, diode is on, and for all these voltage, of course, diode is off. So I can write mathematically Vi, so greater than 1.4 on, Vi less than equal to 1.4 off. So input signal greater than 1.4 on, diodes, both the diodes are on. Input signal less than equal to 1.4, both the diodes are off. And then we determine the time corresponding to this intersection. So we know that this line intersect the signal here and here. So T1 is the time when Vi is equal to 1.4 occurs. T2 is the time when Vi is equal to 1.4 occurs. So mathematically we can write T is greater than 0, less than equal to T1, Vi is less than equal to 1.4. From T1 to T2, T is greater than T1, less than T2, you see Vi is greater than 1.4. Again, T2, T is greater than T2, less than T by 2, Vi is again less than 1.4. So in that case, diode is, since it is less than 1.4 is off, on, off. So that is how we found out the range in terms of voltage when the diode is on and when the diode is off, and range in terms of time. The duration or time interval when the diode is off interval, and it is on interval. So that is graphically as well as mathematically. So next step would be to determine the input output relationship when the diode is on, when the diode is off.